SwayamPrabha. Digital India. Educated India.
So, you can integrate these equations from T to Tf, and of course, from Pi to Pf, and of course, here if this Cp is not a function of temperature, then this has to be within the integral. If it is not, then we can take out this integrals. Similarly, another way of representing this entropy change in terms of Cv. So, here it is Cv, and other side is, instead of P we have nR ln dV by V. So, in a similar way, ds can be replaced with delta S. So, these two expressions gives us the workable model or workable expressions to calculate the entropy change. So, by workable model I mean we know the thermodynamic coordinates, and in our case either it is a pressure temperature or it is a temperature volume. So, in a both the way, if you know any two parameters, then we can also find out the entropy change. Then after this entropy evaluation, we are now going to talk about something on temperature entropy diagrams. So, I mentioned that when you talk about work transfer in a PV diagram, so any process goes from 1 to 2, and we say if you drop normal, so you can say area under this curve is nothing but work transfer. In the same logic, we are going to say, because W is equal to integral of P dV. In a same logic, we can represent the temperature diagram, and for same process 1 to 2, and our expression shows that this QR is nothing but, or Q12 integral of T ds. So, when you say integral of T ds, so it means that area under the temperature entropy diagram represent the heat transfer, area under PV diagram it represents the work transfer. Now, on here we are going to introduce some terms like, if you have this temperature entropy diagrams, we may have a situations where for an isentropic process in a vertical line, other may be an isothermal process in a horizontal line. So, such a process, and if you talk about this is nothing but your isentropic. As you can clearly see, there is no area. So, it means that in isentropic process your Q is equal to 0, and when you go for isothermal process, this diagram will be a rectangle. So, it is a isothermal process, and the area under the diagram will be a rectangle. So, to summarize this, what we can say, area under the diagram represent the heat transfer to or from the systems. In a TS diagram, an isentropic process is nothing but a vertical line, and we call this as isentrope, and this isothermal process is referred as a isotherm. And why it is important? Because it is particularly convenient for representing all idealized cycles of heat engines. Now, moving further, there are some other viewpoints, like how this temperature entropy diagram is again linked with the Carnot cycles. So, for example, if you have some initial state I to F, and you are going this in a one of the reversible path R1 and another reversible path R2, there may be infinite number of reversible path possibilities, but however, and as you can say, the net work for this cycle will be nothing but the area under this closed curve. Net heat transfer during this process will be the area under the closed curve. Now, one of the important thing is that we can talk about Carnot cycle like talking about the two upper limits, and we can draw a rectangle. So, the upper limit of temperature is this. So, I can say AB line we can draw a isotherm, another line which is DC, which is the lowest point on this curve. So, I can talk about another line. So, ABCD is nothing but a Carnot cycle consisting of two reversible isothermal processes and two reversible adiabatic process. However, we have this R1 and R2, they are nothing but the reversible path or reversible processes. So, once you know the heat transfer from this TS diagram, we can easily calculate the work transfers. Then thermal efficiency for the engine can be evaluated. Again, moving further, some important significance for any entropy diagram we can draw. So, I have already demonstrated what is an isentrope, constant entropy line in a TS diagram, what is an isotherm, which is a constant temperature line in a TS diagram, and there are other processes like we can have a isochoric process. So, your volume is equal to constant. So, this curve goes in this manner. There are isobaric process where pressure remains constant. We can also talk about an adiabatic process. We can talk about adiabatic process where Q is equal to 0, whether it is not an isentropic, but it is a adiabatic process. We can also talk about polytropic process. All these processes can be talked about by giving the definition PV to the power n is equal to constant. So, this part I have already mentioned, based on the exponent n, this path can be specified. But one more thing, important thing is that if you recall our expressions of entropy in terms of Cp and in terms of Cv for specifically for isochoric process and isobaric process, one important consequence it gives that for an isobaric process we say dP is equal to 0. So, this particular expression now becomes dT by ds at constant pressure is T by Cp, and similarly for an isochoric process when dV is equal to 0. So, dT by ds at constant volume is T by Cv. So, what it says is that dT by ds is nothing but the slope of this diagram. So, if it is a constant pressure process or it is whether it is a constant volume process. So, the slope of the constant pressure and constant volume process on a TS diagram is independent on the nature of the systems. So, here you can say T is your absolute temperature, Cv is your property, the specific heat capacity of the medium. So, for and these are independent on any other nature of the hydrostatic systems. Now, let us talk something on entropy which has relation with respect to reversibility. So, we have mentioned here that there may be infinite number of reversible processes that we can view, and for that we can say, and in each process we can calculate the entropy change. What important significance is that we are talking about entropy of two things. One is entropy change for the systems and entropy change of the surroundings, and change of entropy of system and surrounding will consist and will give us the change in the entropy of for the universe. So, this is exactly what we are going to find out, that what is the meaning of the sum of these entropy changes, or in other words we are going to say that physical meaning of entropy and significance of this all entropy changes can be estimated. So, for example, if you consider a reservoir that absorbs Q amount of heat at temperature T from any systems, so you can say that entropy change of the is recognized as Q by T. Now, that is for the systems. We can also say that what happens to entropy change of the universe. So, a system, if you have a system and we have the surroundings, So, both constitutes this universe. So, what we are looking at that, for example, we are considering a process which is accompanied by flow of heat between a system and a set of reservoirs consisting from Ti to Tf. So, we can say that as if we have a system and there are some reservoirs R1, R2, R3 and so on, and this of course all the reservoirs are within the surroundings. So, what we do is that system undergoes a change of state from Ti to Tf. Now, the final stage happens in a multiple number of steps, that means first the system interacts with reservoir 1, next it interacts with reservoir 2 and next it interacts with reservoir 3, and in this process it has delta S1, delta S2 and delta S3. So, all these things are entropy change when the system is undergoes the reservoir 1, 2, 3, and there may be many number of reservoirs like this, and through the process what changes happened, the system undergoes from Ti to Tf. But in this process, through this process there are also change in the entropy for reservoir 1, 2, 3. So, summing of all these things will talk about the total change on the entropy of the universe. So, we will now calculate how we are going to evaluate it. So, for that we are talking about two situations, like in one case your this system and there is a reservoir. So, we will consider only one reservoir in this case. So, here heat is absorbed by the system, that means I am taking heat from the reservoir. So, heat is absorbed by this system. So, we say dQr. In another situations we can have a reservoir and we have system. So, here heat is rejected from these systems. So, we say it is a minus dQr. So, from this what we can say, this is nothing but ds of system and this is nothing but ds of reservoir. Similarly, here delta S of system or ds of system and ds of reservoir. So, one case it is negative. So, in this case when heat is rejected by the system is negative, when heat is enters into the system it is positive. So, based on that one can have appropriately use the positive and negative signs, and and finally we can calculate the entropy change of the universe in both the cases, and it happens to be 0 because all are reversible path and entropy change of the universe is 0. So, in a reversible process the change in the entropy is always 0. So, this is the consequence that we can make, that when a reversible process is performed the entropy of the universe remains unchanged. Now, when you say a process undergoes a reversible path, we can say that we can calculate this entropy, but there are situations that always reversible path is not possible. So, we have to rely on all natural processes and they are mostly irreversible. So, what we can view this particular analysis is that, so in order to analyze a irreversible path or in order to introduce a concept of BP reversibilities, what has been done is that first you write the expressions for entropy change, that is SF minus SI, that is final state minus SI initial state, is the cyclic integral of dQr by T, which is dQr is nothing but your reversible heat transfer. Now, same expressions can be used for irreversible path with some change, like, so when I say a process changes from one say temperature entropy diagram, let us say it goes from a reversible process, so 1 to 2. Now, if same process, if I want to have it maintaining initial state and final state same, if this, let us say it is reversible path R1. So, in a reversible path your initial state and final state are always in equilibrium. At the same time all intermediate states are also in thermodynamic equilibrium. But what happens if it is an irreversible path, we can only assume that initial state and final state, they are in equilibrium. So, this continuous curve we normally represented in a dotted line. So, that we can say that in a process 1 to 2 we can take either from 1 to 2 and also from 2 to 1 we can travel. So, in both way the process can occur, but whereas in a irreversible path the process can occur only in one directions. So, same expression same states, if I represent 1 and 2. So, I normally represent in a dotted line, and this is nothing but your irreversible path. So, it means that process can occur only from 1 to 2, not from 2 to 1. So, this is the basic difference, but in terms of end results what we are assuming as if this initial states and final states are in equilibrium, and what we do each year we can calculate the heat transfer from 1 to 2. So, we can write it as a dq, but this is not a reversible heat transfer, but the path is as if we are calculating this for a reversible process. So, R we are putting it here, that as if this value is calculated for a reversible process. Now, let us see what happens these two numbers. So, already we proved that entropy change for the universe is 0 for all the reversible process. Now, we are going to calculate what happens for irreversible processes. Now, these irreversible processes are nothing but your natural processes, and they can be categorized in 4 segments. 1, processes exhibiting external mechanical irreversibility, processes that case 2, processes that exhibit internal mechanical irreversibility, that means external means outside of the system or surrounding gets affected, processes that exhibit internal mechanical irreversibility, that means only internal structure of the system or internal change of the system happens, processes that exhibit external thermal irreversibility. So, it is both are mechanical and this is a thermal, that means outside only thermal change has happened, and last one is processes that exhibit chemical irreversibility. So, all these processes we are now going to discuss. So, first one is processes that exhibit external mechanical irreversibility. So, there are some processes, there are 2 categories of the process. One is isothermal dissipation of work through a systems, in which the work which remains on state, that changes into internal change of the reservoir. So, and here there is no change in the entropy of the systems, because the thermodynamic coordinates do not change, but change of entropy for the reservoir. So, typical examples are like, so if you look at this first law, you start with a first law, dq is equal to du plus dw, and we say it is a process is isothermal process. So, q is equal to w, because du is equal to 0, and when q is equal to 0 we can write dq is equal to Tds. So, we can write delta S of the reservoir as W by T, and delta of the system is 0, because system is there is no change in the internal change of the system, because thermodynamic coordinates do not change. So that delta S universe can be calculated as W by T. In another case, same change of state happens, but the process, and we call this as external mechanical irreversibility, but the process involves adiabatic dissipation of work. So, the same equation can be used, but with a viewpoint that this delta S systems we can calculate, because the system undergoes an adiabatic change from final states to initial states. So, we can calculate this delta S system as Cp times ln Tf by Ti, and the surrounding delta S surrounding is 0, because since the process is adiabatic, no change in the change of heat transfer to the surroundings, there is no change flow of heat to the surroundings. So, from this we can calculate again delta S of the universe system plus delta S of the surroundings, we can calculate. So, typical examples there that involve the friction from the rubbing of insulated liquids, inelastic deformations, irregular stirring of viscous liquids. There are multiple examples in this category. In another case that involve the transformation of internal energy of the systems in an adiabatic wall into mechanical energy and then back to the energy, internal energy again. So, this process calls as okay. So, this is another example where again adiabatic, the processes that occur that exhibit internal mechanical irreversibility. Other case was the external mechanical irreversibility, and this case was internal mechanical irreversibility. So, internal and this they are characterized by the fact that the transformation of internal energy of the system is done which are enclosed by closed adiabatic wall. What it means is that, now let us talk about one particular example, ideal gas rushing to the vacuum, and such a process we call this as a pre-expansion. What we have is that we can have an adiabatic enclosure and one side, and there is a partition, and one side we have vacuum, and we have other side we have some gas. So, what happens here, that the gas, when the partition is removed, the gas suddenly rushes into the vacuum. So, what happens here, the volume of the gas changes from initial volume Vi to final volume Vf. But in this process what happens to the surroundings, because since it is an adiabatic enclosure, so there is no change in the entropy for for universe, because Q is equal to 0. And because of this reason, what happens, we can revisit our basic equations, dq is equal to du plus dw, and this dqr we can by t, because is equal to, then if you divide this by t, then we can write dqr by t is equal to p by t into dv, because du is also 0 here. Now, from these equations we can use these ideal gas equations and to frame out the entropy change of the systems. Then we have entropy change of the surrounding is 0, and finally we can calculate summing it of entropy change of the system and surroundings, and here we will find that entropy change of the universe is nr ln Vf by Vi. So, from this equation we can say that Vf is always greater than Vi. So, delta S inverse will be always greater than 0. The third case, which is nothing but the processes that exhibit external thermal irreversibility. So, these processes involve the transfer of heat by virtue of finite temperature difference. So, typical example is that conduction or radiation of heat from the system to a cooler surroundings, or conduction of radiation of heat that remain from a hot reservoir to a cooler one. So, in this case what happens, if you take an particular examples, we have some q units of heat which is conducted from hot reservoir at T1 to a cooler reservoir at T2. So, from this case for hot reservoirs it takes the heat transfer takes place, so it is heat rejection. So, it is minus q1 by T1 because hot reservoir is at temperature T1, and similarly for cold reservoir we can write it is absorbing. So, it is plus q by T2, and from this we can find out the delta entropy change of the universe. So, here obviously we can say it is q by T2 minus q by T1. Since T2 is less than T1, so entropy of the universe is always greater than 0. And last one is a processes which is exhibit chemical irreversibility. So, what happens now, you are moving into entropy change in a chemical process, that could be a diffusion process, that could be a freezing or condensation process, that could be a mixing or solutions or osmosis process or any chemical reactions. And one typical example we can say that diffusion of two dissimilar metals. So, this is just a situation analysis what you do for the entropy analysis for case 2, where we said that there is a gas, and here I can putting instead of gas 1 I can put it as a gas 1, gas 2. There are many gases like this, and there is a partition here and it is adiabatically closed, that means there is no heat transfer. So, here and this side also a vacuum, and with some chemical reaction has happened, because of which pressure has changed and all these gases rushes into this. So, that particular things case 1 which can visualize as if it is a multiple number of expansions, and that expansions are nothing but in an that happens in an adiabatic enclosure with chambers of equal volume. So, likewise we can find out for gas A what happens to entropy change, for gas B what happens to the entropy change. So, this is the for total change of the systems, then total change of the surrounding is 0 because there is no q or q is equal to 0. Then we can find out the entropy change of the universe, and here also entropy change of the universe it has been found there, it is always greater than 0. Now, what we have discussed so far, if you can summarize, that there are 4 particular cases with external mechanical irreversibility, internal mechanical irreversibility, external thermal irreversibility and chemical irreversibility. And for all these cases we have summarized what happens to the entropy change of the systems, entropy change of the surroundings, and summation of these two will give you the entropy change of the universe. So, and for all the cases one important consequence is that delta S universe is always greater than 0 or it is always positive. So, this is the first consequence, that when you calculate entropy for an irreversible process and for universe it is always a positive quantity, and but when you talk about entropy change of the universe for a reversible process it is always 0. So, now we are end of this particular lecture. So, I will try to solve one simple problems just to give what is our understanding. So, the first problem is about the calculation of entropy change and to visualize the concept of a reversible process. How a process can be reversibly heated. So, one typical example which is given here, that there is a unit mass of water which is at 0 degree centigrade. It is brought to contact with a heat reservoir at 100 degree centigrade. So, what we can see here is that we have a set of water, or in this case I can say we have a unit mass of water which is available to us at 0 degree centigrade, and we want to calculate the first case, that when the water reaches to the reservoir temperature, and in this case it is 100 degree centigrade, what will be the entropy change of the universe. So, basically your system will be water and there is a reservoir. So, water is at 0 degree centigrade, reservoir is at 100 degree centigrade. So, I can say it is 273 Kelvin and it is 373 Kelvin. Then the water is in contact with reservoir. So, obviously heat will enter from the reservoir to water. So, we can calculate the what is the heat absorbed by this. We can say Q is equal to m Cp times delta T. So, Q that comes from the reservoir can be calculated. So, m is equal to 1 and here we can write for Cp for water 4.187 kilojoule per kg Kelvin and delta T is 100 degree Kelvin. So, we can say 1 into 4.187 into 100. So, this turns out to be 418.7 kilojoule. Now, we have to now find out entropy change. So, first we have to find out what is delta S for water. Delta S for water, we can write water goes from 273 to 373. So, we can integrate this dq by T and dq is mCp dt. So, we can say mCp times integral of dt by T. This integration has to be performed from 273 to 373 and this is nothing but your ln T. So, mCp ln T that has to be evaluated from 273 to 373. So, this value will be like delta S W we can write as 1.305 kilojoule per Kelvin. Now, delta S for reservoir we can write is nothing but minus Q by T because the reservoir lost the heat and this is 4187.7 divided by temperature reservoir temperature is 373. So, this number is minus 1.122 kilojoule per Kelvin. So, finally, we can say what is delta S of universe by adding these two, delta S W plus delta S reservoir. So, this number will be 0.183 kilojoule per Kelvin. So, you can see this delta S universe is greater than 0. So, this is the first part of the problem. Now, we can move to the second part. So, in the second part what happens, this heating takes place in two stages, first with 50 degree centigrade heat reservoir and second with the 100 degree centigrade of heat reservoir. So, these two stages of heatings will change the entropy of the water. How? We can write this particular integration as dq by T and that from 273 to 50 degree centigrade will be 323 Kelvin, 323 plus integral of dq by T from 323 to 100 degree centigrade, that is 373, and this when you evaluate will be you can write dq is equal to m Cp dt. So, we can take the integration. So, this turns out to be 4.187. So, here we can say m is equal to 1 kg. So, this can be written in this manner, ln 323 divided by 273 plus ln 373 divided by 323. After evaluating, we can find delta S W is 1.305, but delta S R1, that is reservoir 1, is minus Q by T1, and this is nothing but minus 4.187. Q is Cp is Cp is this 323 minus 373 minus 273 divided by T1 is absolute temperature at T1, it is temperature at 1 is 323, and for that number is minus 0.647 kilojoule per Kelvin. Similarly, delta S reservoir 2 would be minus 0.56 kilojoule per Kelvin. So, when you sum it together, so delta S universe would be 0.098 kilojoule per Kelvin. So, what we see is that when you do this heating in stepped manner, that is one with 50 degree centigrade, then to 100 degree centigrade, entropy change of the universe is less. In this case it was 0.183, now it is 0.098. So, it means water is reversibly, if water is reversibly heated, almost there will not be no change in the entropy. So, the third part of the question says that how the water can be reached, water temperature can be reached to 100 degree centigrade with almost no change in the entropy of the universe. So, if that means if you make this water to be in contact with reservoir with very small infinitesimally small change in the temperatures, then we can say the water is reversibly heated. Now, the next problem we will talk about some definition of different thermodynamic properties for an adiabatic process. So, the problem statement goes that a fluid undergoes a reversible adiabatic compressions that from initial state 0.8 megapascal and initial volume 0.03 and final volume 0.05 meter cube, and it follows a loss Pb to the power 1.3 is constant. To do this, what we can draw first is PV diagram that talks about this path, and the process goes from 1 to 2, and it is P v to the power 1.3 is equal to constant. So, we can say P1 V1 to the power 1.3 is equal to P2, sorry, I will write it as n, where n is 1.3, P2 v to the power n is equal to constants. So, we know P1 0.8 megapascal, V1 0.2 meter cube, V2 0.05 meter cube. Then from these equations we can find out P2 is P1 into V1 by V2 to the power n. So, all these numbers we know. So, this will give you what is P2. P2 will be 4.848 megapascal. So, we know P2, we know P1, we know V2, we have all the parameters. Then we have to recall dH is equal to TDS equation. TDS is equal to dH minus V dP. So, in this is a reversible adiabatic process. So, this goes to 0. So, we can find out dH is equal to V dP. So, from this we can find out heat transfer, that is enthalpy transfer, H2 minus H1 is equal to integral of V dP from 1 to 2. Now, V we can write as integral of 1 to 2 P1 V1 to the power n divided by P and dP. Now, when you do this integral, we can say that H2 minus H1 as n times P2 V2 minus P1 V1 to the power n minus 1. Okay. So, this is the expression of enthalpy, where and here we have n is 1.3, P1 V1 P2 V2 all are known. So, we can find out H2 minus H1 is 357 kilojoule. So, enthalpy knows, then we can find out internal energy, then we can U2 minus U1, U2 minus U1 is H2 minus H1 minus P2 V2 minus P1 V1 whole bracket. So, we can find out U2 minus U1 as 274.6 kilojoules. So, enthalpy known, internal energy known. Entropy ds or H2 minus S1, that is equal to 0, because it is an reversible adiabatic process. Heat transfer, now Q12 also 0 because adiabatic. Then next is work transfer. So, it is nothing but W12 is equal to Q12 minus delta U. So, delta U we already know here. So, Q12 is 0. So, we can say W12 becomes minus 274.6, negative sign of this, kilojoule per kg, sorry kilojoule. Okay. So, from this problem, this gives the basic definition for a given process, how this properties value can be evaluated. So, with this I conclude this lecture for today. Thank you for your attention.